Let's talk about types and their sizes. We'll focus on fundamental data types and then get into a couple of the modifiers. I'm going to create a main .c file. And in that main, I'm going to start off with a header here that kind of just describes. I like to put a header in all my files. And it just kind of describes the purpose of the file. Demonstrates the sizeof operator. Or function, I should say. Okay. And I'm just going to make this come out a little bit farther. There we go. And same with this bottom. I like boxes. I know this is probably uncouth, but this is the way I like to do it. Okay, and then just about every program you write is going to have include standard IO, stdio.h, and then int main, open brace, close brace, and return 0, just right off the bat. And don't forget your semicolon, my Python friends. Okay, now the fundamental data types include, and I'm just going to put a comment right here, char, short, well, I'll do int, long, and float, I believe. Okay, so anyway, let's take a look at these, how long each of these are. So the way I'm going to do that is I'm going to just say, I'm going to use the printf function, printf, and I'm going to start with some print conversions, right? So the first one I'm going to do is a string, because I'm going to have a string argument that says what we're actually measuring the size of with the sizeof operator. And that's going to look like this, right? It's going to have percent 20, and then S, and I'm going to do a tab, and then another percent, and then 2 LU, which is LU, which is I have to go back and look at that thing, what LU means, right? So and then let me see, /n. Okay, and that's going to give me my line return. Now here's the message I'm going to say. I'm just going to show like size of, and then the type I'm measuring, and then I'm going to actually call the sizeof operator, or the sizeof function, with that type. Okay, and then don't forget your semicolon. Now, the way this works is this is going to return, right? You can see when you hover over this function, a 1UL, right? Unsigned long, okay? So when that unsigned long, when this returns, right? So that's why we've got this format specifier right there. Okay, so anyway, when we run this, we'll see the value. So let's go ahead and run this. All right, so the way that we do this is obviously you have to compile. So GCC, make sure you're in the right directory with your terminal. GCC-O, main.o, and then main.c, okay? So we compile it, and then to run it, /m, and just hit tab. And there we go. So we have 1 byte for a char, okay? We have 1 byte for a char. Now, let's do an int. Okay, so an integer is like the fundamental data size on just about every machine, right? So if you have a machine that's a 64-bit architecture, I will see right here how many bytes it returns, right? So printf, let me just copy this whole thing because it's pretty much the same. Okay. That's why C is like, was one of the first, not probably the first, but, a portable language, because it allowed the language to be detached from the machine, right? So then all the sizes of each particular machine could be specified separately, right? So int, all right, and int. All right, so save, compile it, and run it. So 4 bytes, okay, so 32 bits. So each byte is 8 bits, and we have a 32-bit integer. Now your machine architecture may support a longer fundamental, I would say, a word size, right? So a word, if I'm not mistaken, is, like your fundamentally addressable, well, your memory can be addressed by byte addressable. A lot of memory is byte addressable, right? But generally speaking, your memory has a fundamental size. So if you have like a 64-bit architecture, and your memory is 64 bits wide, that's your word size, right? And then it may be more efficient to load in the entire word into the processor and then extract the particular integer that you're looking for, right? Or char, right? So sometimes these things get stored depending on the way the compiler generates the object code, the way that the machine architecture is laid out. Some of these, if you declare variables of different types, they may be packed together in a big old long word, right? And then that whole word has to be read in to the processor, right, to extract the data from those bits. That's pretty much beyond the scope of this course, right? You would take an architecture class, a computer architecture class, right? Let me go ahead and copy this. Okay, now let's do long. All right. So long should be twice as long as an integer. So long. Okay. Save that and return and run it. And there we go. So 8. So we have 64 bits for a long. Okay. Now, let's do a float. Save that. Compile it. Run it. So we have 4 bits for a float. And if we wanted a bigger float value, then we had to go to double. So let's do this. Double. Double. I'll add this up here too as fundamental type. Save. Compile. And run. So, okay, so your char is 1 bit. Now, in this char, you're going to be storing ASCII character. It's equivalent to an integer, except it's only 8 bits wide, right? So it'd be equivalent to like an unsigned short. Okay, and then size of int, you got 4 bytes. The long has 8 bytes. So obviously you can store more information in a long variable than you can in an integer variable. Okay, a bigger number essentially. And then you can store a greater precision number in double than you can in a float. You've got 8, you got 8 bits to do so. Okay, I could have a whole like almost course on just like precision. At least a whole video, right, on the difference in precision and the IEEE standards. All right, but anyway, just know that, you're storing integer values in these int types and int and long, and you're storing floating point precision values in these in a float or a double, and you're storing char individual chars in a char type, right? So a string essentially, in C, unlike Python where you have a string type, right, and C# we have a string type. A string is simply an array of characters. Okay. All right. So now let's use some of the modifiers. So some of the modifiers on these types would be unsigned versus and signed. Okay. So like you'd have an unsigned. I guess did I do short? I didn't do short, right? Let's put short up here. And let's do short in front of, I forgot short, right? So, well, we got short int. Now short and short int are equivalent, okay? Short is almost like a modifier, but I don't know. In retrospect, I would say your fundamental types are, char, int, float, double. I'd have to go even review that one myself, right? But then you've got short, and then you've got the long. Okay. So let me just go ahead and squeeze in down here the short. Oops. Let me copy this line. And we're going to change this to short. And we're going to change this short. Save it. Compile it. Run it. Okay. So a short, we have a char, 1 byte. A short is 2 bytes, 16 bits, 32 bits for the int, 64 bits for the long, 32 bits for the float, and 64 bits for the double. All right. Now, you also have modifiers, like I said, signed and unsigned. The difference between a signed and an unsigned is unsigned, there is no signed bit. So the leftmost bit, right, or the most significant bit, I suppose, right, from right to left, right being the most significant bit, is reserved for an unsigned. That's used as part of the whole value, right? So there is no negative number for an unsigned value, right? For a signed value, that leftmost bit is reserved to indicate the sign. All right, so let's go ahead and just print. And we'll do unsigned short. So all the integer types above, right, that we just did are signed. Okay, so unsigned short. Now let's run this and compile it. It should. There will be no change in the size, right? So unsigned short is 2, and a short is 2, right? The only difference is that the leftmost bit is reserved for a signed short to indicate whether it's positive or negative. So you have a range of negative numbers with a signed integer, but you can't store quite as large of a positive number, right? In fact, it's like the number of bits 32 minus 1, something like that. Okay, now we come up to let's just do this. Let's go ahead and see what happened. Seems I'm getting my paste. Okay. So let me just copy this line here. Let me close this. And copy that line. And we'll do unsigned int. There's not going to be any changes in these sizes. I'm just kind of going over the types at this point. Unsigned int. And I'll go ahead and do the next one. So unsigned long. And then unsigned long. Okay. And let's run this. Compile it. Run it. Okay. So you can see that there's no difference in the number of bytes for an unsigned long versus a long. The difference is in the fact that an unsigned can only have positive number and a signed can have negative and positive numbers. All right, next, let's print out. That's pretty funny. I don't know why that thing is taking that. Okay, Control C, Control V. All right, now here I'm just going to print out. I'm just going to print out this. Print. Give me a separator. Now let's declare some variables, right? So let's say we have int a. Actually, I'll tell you what. I'll do that in another video. But what I will do is, yeah, I'll do that in another video, right? So we have our types and sizes. So in the next video, we'll declare some variables of these different types. And then run the sizeof operator on them again. We'll also declare a few arrays of these types, and we'll see how the size of the arrays compares when you have arrays of differing type sizes. All right, see you in the next video.